Hello, everyone. Welcome to the 21st webinar in the Joint Tran-SET webinar series, which will cover different projects related to practical applications for novel cementitious composites from three quite different perspectives. Okay, today we're privileged to have three transportation experts presenting in this webinar. We will have three 15 to 20-minute presentations. First, Dr. Gabriel Arce will discuss culvert repair with engineered cementitious composites. After that, Dr. Saiidi will present on smart and damage-resistant materials for resilient bridges, from research to deployment. And finally, Dr. Newtson will present on ultra-high-performance concrete bridge deck overlay from the New Mexico's experience point of view. We will save questions until the end of the three presentations for a 15-minute group Q&A. You can type your questions anytime throughout the session. Okay. Without further ado, I will introduce our first speaker, Dr. Gabriel Arce. Okay, Dr. Gabriel Arce is a research scientist at the Virginia Transportation Research Council. He earned his PhD in engineering sciences with a concentration in advanced materials and sustainability at Louisiana State University. Dr. Arce has more than 8 years of experience in the field of advanced concrete materials and has worked in the development of self-healing concrete technologies, the characterization and microstructure evaluation of cementitious materials, and the advancement of engineered cementitious composites. Dr. Arce has published more than 30 research articles and holds a patent on the development of ECCs incorporating agricultural waste products. Dr. Arce serves as a member of TRB AKM 50 Standing Committee on Advanced Concrete Materials and Characterization. Furthermore, he's an associate member of ACI committees 236 on material science, 239 on ultra high performance concrete, and 564 on 3D printing with cementitious materials. He's also an associate member of American Society of Civil Engineers. Dr. Arce, I will turn it over to you now.
Thank you very much, Daniel. Let me share my presentation. Okay, can you see my presentation correctly?
Yes.
Very good. So good afternoon to everyone. Today I'm going to be speaking a little bit about the work we have done at BTRC, myself and my colleagues, on culvert repair with engineered cementitious composites, specifically with regards to metal culverts. Okay, so we're going to start with a quick introduction on culvert deterioration and repair. So culvert deterioration, it's a major problem here in Virginia. In particular, again, we're talking about corrugated steel culverts. We have about 1,900 of these metal culverts in the state. Around 7% of these culverts are in poor conditions and require rehabilitation. About 56% of these culverts are in fair condition. In the next coming years, they could transition to poor condition. And this deterioration usually occurs because of corrosion of these culverts. These culverts are usually made out of galvanized steel, which gives some corrosion resistance. Nonetheless, over time, with the water, they corrode. And also because of the aeration of not just the water, but all particles that go in this water and gravel, etc. Now, if you want to replace these culverts, is fairly expensive and often require temporary closure of the affected roadway. So this is, again, a very significant problem for us here in Virginia, and very likely in many other states in the United States. Okay, so how this deterioration occurs. At early stages, only limited damage occurs at the invert of the culvert. The invert is the bottom portion of the culvert. And of course, that's the area where the water is always flowing and therefore it's more susceptible to damage. And this is an image that I'm showing of one of the culverts here in Virginia with some minor deterioration of that bottom portion of the invert of the culvert. Here, you can see a zoom-in picture on this deterioration. As you can see, you start losing a little bit of of the surface of these culverts. Next, at later stages, if nothing is done, extensive damage can occur. This image right here is by some research done by Peter and Moore. And this is a culvert that was extracted from the field, and then they rotated the culvert so that you could appreciate, all that damage in the culvert. As you can see, you have wall loss and perforations that occur, and the structural capacity of this culvert is significantly affected. So again, if we do not repair these culvert inverts, this damage can extend and can be very problematic. So now regarding culvert invert repair. So as I mentioned, at early stages of deterioration, only minor damage of the invert occurs. So restorative maintenance at this point is possible and is appropriate. And this is to protect, that invert for further corrosion, further abrasion damage. At DDOT, some repairs were previously done, which consisted of pouring or paving that invert with a 4-inch thick layer of concrete that was reinforced with wire mesh. The 4-inch thickness and the wire mesh were used so that cracking could be prevented. Because of course, if you have an invert repair with a concrete material that cracks, water can continue to flow through those cracks and then be in contact with the existing steel culvert and continue the corrosion, the rapid corrosion deterioration. Now, the problem with this is that this is a very thick repair, these 4 inches, and that adversely affects the water flow, flow capacity of this culvert. So this is not an optimum solution. And ultimately, what is necessary is a thinner, more durable repair for these inverts. Now, whenever we have more than just a minor invert deterioration, but we have a more significant deterioration that actually requires structural repair, one interesting option for structural rehabilitation in this case is the use of spray-applied pipe liners. These are rapid and cost-effective solutions in which basically you use a cementitious mortar. This is usually fiber reinforced and is centrifugally sprayed. As you can see in this image, this is the culvert. You have the host, metallic pipe, and you use this spinning head. As you can see, you pump the concrete to that spinning head, and due to the rotation of the spinning head and centrifugal forces, the material is expelled to the surface of the hose pipe. And you can build a cementitious pipe inside of the hose pipe. Usually a thickness of around 2 inches is used for these type of repairs. This is an image of the repair being completed. And finally, this is another image of multiple of these culverts that were repaired using this technique.
This is me. I'm so sorry.
Yeah. Excuse me? Okay. So I'll continue. So now, what is the problem with this technique? As you can see, it has been done. We have had some demonstration projects in Virginia. But the problem is that in some of these repairs, we have observed some early cracking. And this is an image right here of how this cracking looks. And why this could be a problem when you do the entire culvert repair. This is a structural rehabilitation. So if you have cracking, it really matters what type of concrete you have there, what type of behavior of this concrete, because of the fact that you need to hold that load carrying capacity. And I'm going to talk a little bit more about that in the next slides, and why ECC, either for the invert repair or the entire culvert repair, it's a very interesting solution. So, okay, let's start with the ECC for culvert repair and why we believe this is a very interesting solution. To introduce the behavior of ECC, I would like to start by showing the behavior of different cementitious materials. So specifically when tested in tension, right? The tensile properties. So imagine we're doing a tensile test, right? Right here, we have a tensile stress versus strain graph, right? We have this concrete material at time 0, and this is imagine it's a deformation control test. So you are pulling this concrete material, right? So at the beginning, no strain, 0 microstrain, nothing's happening. You continue deforming the material, 25 microstrain, the stress response is about 100 psi. You continue until suddenly, when you reach about 100 microstrain, which would produce about 400 psi of tensile stress in the concrete, the conventional concrete would crack. Now, the question is, what happens after this crack? If it is a conventional concrete material without any fiber reinforcement, what is going to happen is the following. You're going to have a brittle, immediate failure of this material. And that, again, imagine the culvert repair, when you have this structural repair. If the concrete material that you have there does not have any fibers and you have a crack, you know that that concrete can no longer hold the load. So this could be very problematic if the host pipe, the host metallic pipe, further deteriorates to a point in which the concrete material actually has to hold the load. Next, let's see what happens when we have fiber reinforced concrete. If we have a conventional fiber reinforced concrete, after this first crack, what is going to happen is something like this. You're going to have a strain softening behavior, meaning that after that first crack, you have a residual load carrying capacity. Nonetheless, this capacity is lower than the original concrete material prior to cracking. And if you continue deforming these materials, the load will continue to go down, and that crack will continue to open until finally you have a complete rupture of the material, a complete failure. So it's important to notice that similar to conventional concrete, this fiber reinforced concrete, after the first crack, it is already in a failure regime, right? That's why I have this as a plot with a dashed line. Now, interestingly, the ECC, engineered cementitious composite, behaves rather differently. So how does the ECC behave? After that first crack, you continue deforming the material, and you actually have a phenomenon called pseudo-strain hardening, meaning your material can hold more load after the crack. And how does this mechanism occur? It occurs through this process of multiple crack formation. And this strain hardening is called pseudo-strain hardening, to be differentiated with the strain hardening observed in metals, which is based on the dislocation of atoms. This strain hardening in this cementitious system occurs because of this phenomenon of multiple tight microcracks formation that allow this material to deform. It's important to mention that these cracks are very tight, and that's important for durability. Sometimes you can barely see these cracks with your eyes. Now, interestingly, you continue deforming this ECC, and it continue producing more tiny cracks, and the load capacity continues to increase. Eventually, you reach to a point in which the material fails. One of these multiple cracks will grow, and the material will fail, similar to a conventional fiber reinforced concrete. But again, imagine the repair that we were talking about in the field for these culverts. If you have an ECC material, this is a very resilient repair, because even if you have that some type of cracking, you know that these cracks are stronger than your original material prior to cracking, and it will be able to hold the load. So it's a very resilient system. Now, how does this mechanism occur? How this ECC came to life? So this ECC was first developed by Professor Victor Lee. In fact, in the early 90s, the development of this material started, and there has been a lot of development in the past few decades on these materials to make them enhance their properties and make them more practical and more cost-effective. How do you design these materials? These are designed based on fiber matrix micromechanics principles and fracture mechanics principles. In a nutshell, what you do with these principles, or the insight that these principles give you, is that you need to use fibers with high tensile strength. And also, you need to control the bond between the fiber and the matrix, the cementitious matrix. Contrary to the belief, usually when you design a conventional fiber reinforced concrete, you try to maximize the bond, get the highest bond possible of the fiber with a cementitious matrix. But in ECCs, this is not the case. You need to have a balanced bond so that the fiber can pull out of the cementitious matrix. And this allows for this multiple cracking behavior of the ECC and the ductility. Also, what these principles tells us is that we need to design a composite where the cementitious matrix is very brittle. And again, this is also goes against to what we typically want to achieve in concrete materials. We want actually a concrete material that does not crack. Well, here in the ECC, you want a cementitious matrix that is prone to cracking to enhance this pseudo-strain hardening behavior. So this is a very interesting, design theory behind these ECCs. And when designing these ECCs, you can be very rigorous and do fiber pull-out tests and do fracture toughness tests to obtain these design parameters and truly optimize these systems. Or also, based on some, literature that exists, you can start by using proportions of material that have already been used and experiment in a trial, trial and error type form. These are very, very interesting systems. And I would like to go even more deep in the explanation of these concepts, but I think it's beyond the scope of this presentation today. So in summary, why engineer cementitious composites? First, superior mechanical properties, have this robust strain hardening behavior that we talked about, unmatched ductility to any other cementitious material. You can see this image right here, how ductile these materials are and how they can bend. And that's why usually they're regarded as bendable concrete. How much, is the ductility in tension? Usually about 200 to 800 times more than that of conventional fiber reinforced concrete. And about 5 to 20 times more tensile ductility than UHPC, which is a very popular material being used in repairs recently. Also, it has unmatched crack controllability. Cracks in ECC are steady state controlled to usually less than 60 micron. Why this is very important? Because this allows these cracks to be self-healing. Concrete has autogenous healing properties. However, these autogenous healing capabilities are usually effective only with tiny, tiny cracks. This range of crack size is appropriate for this healing. And also, it has been demonstrated through research that cracks around 50 to 100 micron do not allow for the increasing permeability of the cementitious system. So, in short, these cracks in ECC are not a problem for durability. Also, for context, cracks in UHPC, for instance, are usually greater than 100 micron. And in that case, if you have a UHPC with this type of cracking, you can actually reduce the permeability of the system. This is an image just to illustrate that multiple cracking behavior in ECC. This is a section of one specimen that was tested in tension. As you can see, 3 inch by 1 inch to give a sense of scale. And this is at failure. And you can see all those cracks, how tight they are held together. So it's very interesting, this ECC material with regards to crack control. And ultimately, all these leads to an enhanced structural capacity, safety, durability, and resiliency of the systems that you repair with ECC. Now, let's talk about the application of the ECC for the culvert invert repair. As I was mentioning in the beginning, when the deterioration is not that advanced, you can repair the invert in a restorative manner to prevent further deterioration. Previous work by Oshilderim and Sharifi, these are colleagues of mine at BTRC, focused on the repair of only the invert with the ECC. There's a technical report, BTRC 21R5. This report you can access to it online in the web page of BTRC. And you can get all the details about what this project, this successful project was about. In summary, what they developed is a repair technique for the culvert inverts, in which they started by placing a biaxial geogrid in the invert of this culvert. The purpose of this geogrid was to first allow for the material to stay in place. The ACC usually is quite flowable, and also provide some reinforcement because this is a very thin repair. And after that, they sprayed the invert with a thin ECC layer, about 1.5 to 2 inch thick. This is an image of the work of the repair of one of these inverts, and you can see the culvert there, you can see the geogrid, and you can see how the workers are spraying the ACC into that invert. And this is the finished product. Now, in this work, they completed 5 repairs successfully. And to date, this was done 5 years ago. So to date, all of these repairs are performing very, very well. Now, based on the success of this work, now BIT guidelines on restorative maintenance and structural rehabilitation of existing culverts has implemented this method. And you can see here in the image part of this document, in which they detail precisely how this repair has to be done with the geogrid and the ECC. Another interesting thing, we're now trying to update this repair technique to basically do the same, but without the geogrid, because the geogrid is an additional step which requires labor and cost of the material. And this revised technique, which actually the very first time we tested this was yesterday, is the same repair, but now we use an ECC material that has greater shape stability. It's a thicker type mix. And you can see the image from yesterday from the repair. And we were able to successfully repair the invert without having to use this geogrid. And hopefully in the future, I can tell you how it is performing, right? But so far, it has been a success. Now, next, I want to talk about research in progress, and this is particular to the repair of the entire interior culvert with ECC. So first, I want to mention what are the challenges, because this is actually quite difficult. When you do the repair of the invert, gravity in a way is your friend to hold the system in place, right? But when you want to do the entire culvert, especially when you are spraying into the top of the culvert, gravity will try to pull this material down, right? And it's difficult to be able to generate these thickness buildup. So one of the challenges of this is having to change the workability of this ECC. First, to be able to successfully be sprayed, that you need sufficient workability, but then it has to have the rheological properties to produce that thickness buildup as you're spraying, especially when you spray overhead. Then fiber dispersion is challenging because these mixtures are very low workability mixtures. So it's very difficult to disperse the ACC fibers in these mixtures. Practicality and cost is also an issue, especially with these repairs that we want to implement widely in the field. Some components of the ECCs traditional ECCs are expensive and impractical. One example is the type of sand that is used. ECCs don't use coarse aggregate, only use sand. And the sand that is used is usually a very fine particle sand. It's a microsilica sand. This is very expensive and just not widely available. So we need to find alternatives to that. So how are we trying to address that with the research in progress? We have a new research project that started about 6 months ago that is exploring this. We are testing some high performance fibers. These are PBA, which is a traditional fiber used in ECCs, but also ultra high molecular weight polyethylene fiber. Just to give you a flavor for what the properties of these materials are, the PBA fiber typically has that you use for ECC has a length of 8 millimeters, a diameter of 38 microns. and an aspect ratio of about 211. The tensile strength is comparable to that of steel fibers, a specific gravity about 1.3. Now, this ultra-high molecular weight polyethylene fiber, which is a new fiber that we're testing, you can see in the table, I have it as P13 and P6. The number denotes the length of the fiber. These have a much higher aspect ratio than the PBA, much higher tensile strength, much higher elastic modulus, and they're lighter than the PBA. So this is a very high performance fiber, which help us reduce the fiber content of the system while still exhibiting the performance that we're looking at of this material. Also, I have in the last row the properties of conventional polypropylene fiber, just as a comparison. As you can see, these fibers that we use are much stronger than the polypropylene fiber, more stiffer than the polypropylene fiber. And this is important because usually these mortars that are used in the field to do this invert repair, centrifugally sprayed repairs use polypropylene fibers, and these fibers cannot give you the performance that you need for ECC. There are some special type of polypropylene fibers, specifically high tenacity polypropylene fibers that have been used in ECCs, but these are not the ones that are often used in the field. Another thing that we're doing in this research is optimize the mixture's rheology. So we're using a rheometer for this purpose to study scientifically the flow of this material, the plastic viscosity, yield stress, the thixotrophy, which are important properties for this spray material. We're trying to test spray performance. We have a new spray system that hopefully going to help us test how these materials spray in the lab. Also, we do some very interesting tests in the lab. We usually throw this material to the wall first to see how it's sticking to the wall. If it sticks to the wall, as you see in the picture, we're getting closer, right? So this is a very non-scientific way of testing, but nonetheless, it's pretty helpful to guide us where we're at with the consistency of this material. Also, we evaluate tensile properties, and I'm showing this test because this is not a very conventional test that is used. This is a uniaxial tensile test, which is based on guidelines of the Japan Society of Civil Engineers. And from this test, you can obtain, all the relevant properties of the ECCs. You can, measure the elastic modulus, the first cracking, evaluate the strain hardening behavior, and again, obtain all the relevant properties of your ECCs. And finally, we're going to do field tests of this technology and hopefully successfully repair some of these culverts. Also, I wanted to give you a little bit of an idea of how these ECC mixtures look like. Again, this is ongoing research, but the mixtures that I'm about to present you are some of the mixtures that so far are looking promising for our application. These mixtures, the materials that we're using are type 1-2 ordinary Portland cement, fly ash, silica fume. The water to binder ratio is about 0.28. The fly ash content is 55% replacement of cement. Silica fume, we use it at 10% replacement of cement. And then the aggregate that we use is regular concrete sand instead of using this microsilica sand. And this is very important because usually for these ECCs, you want very fine particles because that helps in this pseudo-strain hardening behavior. Nonetheless, we are trying to implement materials that are readily available in Virginia. And the sand to binder ratio that we're using is 0.36, which is very normal for these ECC materials. Fibers that we're using PVA, we're using PE, but for these particular mixtures that I'm going to show you, these are hybrid systems of PVA and PE fiber at 1.5 volume percent. That's a total volume percent of the fibers, which are distributed as 50% of that amount PVA, 50% of that amount is the PE fiber. At mixtures that we use, high range water reducer, air treatment at mixture, and also we have tested the use of shrinkage reducing admixture. So right here are the mixture proportions. This is the mixtures that I was previously mentioning, the ingredients that we're using, the proportions that we're using. And below you can see the mixture ID, so you can understand what this nomenclature means. These two mixtures are basically the same. The only difference that you will see with these two materials is that one uses a shrinkage reducing admixture, the other one does not use a shrinkage reducing admixture. And next, I'm going to show the properties of these two materials. Okay, so these are the properties of these two materials that, again, as I mentioned, these are very promising for the application that we are looking for. The density, as you can see, is very low. These are very light materials. Nonetheless, the compressive strength is sufficient. We're about 6,500 psi. Regarding the permeability of these materials, of course, we want a system that is impervious, so that water cannot continue to penetrate through this cementitious repair and corrode the host metallic pipe. So as you can see, the surface resistivity it's quite high. So this falls in the category of very low chloride ion penetrability. And the rapid chloride permeability test results, as you can see, is about 1,000 coulombs for these materials. So again, very low permeability systems. Regarding the flexural properties, this is based on ASTM 1609, and I'm showing the picture below of the test. The flexural strength of these materials, about 8.8 megapascal for the one without the SRA. And this is roughly 2 times the flexural strength of conventional concrete. Also reported there is the deflection capacity of these materials. Finally, we have the tensile properties of these systems, around 4 megapascal, the strength in tension. And the tensile strength capacity that is shown there is about 2% tensile strain. Important to mention that for a material to be designated ECC, it has to exhibit at least 2% tensile ductility. So these materials are right there in that range. And you can see also for an illustration, I'm showing the test results for the material without the SRA admixture. These are 3 specimens that were tested for each case. And you can see that strain hardening behavior that I was talking about, with all these multiple peaks right here, which are all these tiny cracks that are generated in the process of damaging this specimen. Finally, I want to present also some shrinkage data results. This is not included in the table. And as you can see, when you use this shrinkage reducing admixture, you can reduce the shrinkage of these systems a little bit. These materials have a lot of cementitious content, so they tend to shrink a lot. This is not a concern with regards to cracking, because these are such ductile materials that they will not crack because of shrinkage. But it is important because we want to limit the shrinkage to prevent any type of bond problems with the existing metal pipe, right? An interesting thing about the shrinkage reducing admixture, we not only are using it in this research for the purpose of reducing shrinkage, but also we have found out that this admixture was helping us with the distribution of the fibers. We don't really understand the mechanism of action, but when we use the SRA, it was helping us to get a better prevent fiber clumping in these systems. So again, I wanted to present not just the mixture proportions of these materials, but also some of the properties of these materials to get you a flavor for how these ECCs not just perform, but how they're made of, right? So with this, I am going to conclude my presentation. And if you have any questions, I'll be happy to answer them when it's the time. Thank you very much.
Okay, perfect. Thank you. Thank you so much, Dr. Arce. That was really great, really interesting. Now we'll leave questions as mentioned for the end, right? Now I will introduce the speaker of the second presentation, Dr. Saiidi. Professor Saiidi is a distinguished researcher at the University of California, Los Angeles, a professor emeritus at the University of Nevada, Reno, and a senior principal at Infrastructure Innovation LLC. Okay, he has published over 550 papers, reports, and given over 450 presentations around the world, many as keynote speaker. Dr. Saidi's research has been funded by many national and state agencies focusing on experimental and analytical studies of seismic response of reinforced concrete structures, seismic retrofit, resiliency with novel materials, and seismic response and design of precast bridges for accelerated bridge construction. Dr. Saiidi has received many awards for his research and publications. Dr. Saiidi, I will turn it over to you now.
Greetings, everyone. It's a real pleasure to share with you the results of some of the research that we have been doing for some time. Let me share my screen. And I'd like to thank the organizers for the opportunity to talk to you a little bit about what we have been doing. You see a lot of logos on this slide because the research I'm going to talk about was sponsored by a variety of agencies, including state agencies, the National Science Foundation, and the NCHRP, as well as the U.S. Department of Transportation. So the talk here is about the resiliency of structures, and specifically under earthquake loads. Now, why ECC? How does ECC get into resiliency issue of structures? Well, let's go back to the basic philosophy that we have in seismic design of standard bridges. And by standard bridges, I'm talking about category of bridges that excludes the signature bridges, those long span bridges, cable stayed or suspension bridges. So you're talking about more than 95% of bridges that fall in this category. So the basic seismic design philosophy is that they should not collapse. These bridges should not collapse under strong earthquakes. So if they meet this requirement, then it's considered, the design is considered to be satisfactory. So with that criterion, when the slide in the lower left, the picture in the lower left, shows a bridge that was damaged under the 1994 Northridge earthquake. But you also notice that the bridge has not collapsed. With that requirement, this bridge design was a success. Okay, the bridge did not collapse. It met its design objective. At the same time, if you look at the other picture on the right side, you see the Oakland Viaduct damaged during the 1989 earthquake in Northern California, and the upper deck has completely collapsed on the top of the lower deck. So this would be considered a failure of design. In other words, this bridge did not meet the objective. Now, what is earthquake damage? What is it that we have in the bridges subjected to strong earthquakes? Essentially, there are two types of damage. One is a plastic hinge damage that you see on the left side of this slide, and that's a plastic hinge area. That's the most critical part of the columns under seismic loading. Another issue is the permanent drift. So this is what the slide on the right side, the photo on the right side shows a permanent drift of a viaduct in Japan. And a lot of these bridges were torn down after the earthquake because of the permanent drift that they had, and they were not considered to be safe. So let's talk about the cause of plastic hinge damage. First one, essentially the issue is the low ductility of unconfined concrete. Concrete by itself is a relatively brittle material, so it does not have much tensile strength, and it fails. And because of that, under seismic loading, if we take a column, I'm looking at the plastic hinge of a column, as we increase our seismic loading, the intensity, we have those cracks and we begin to spall the concrete. And as the intensity increases, we have more and more spalling, and we have exposed reinforcement, and eventually we rupture some of the reinforcement. But you notice that concrete has completely fallen apart in the plastic hinge. Now, how about permanent drift? What's causing the permanent drift? The primary source of the permanent drift in bridges under seismic loads is the fact that when the steel yields, it ends up with a permanent strain. So the strain diagram that you see on the left side for steel, it shows a linear part, then the yield plateau, then strain hardening. But once the stress is removed, you end up with a permanent strain, and that permanent strain is the primary source of permanent deformation in bridges after the earthquake that we see. Now, we came across a new material, shape memory alloy, a super elastic shape memory alloy specifically, where we saw the stress strain diagram is a little different than what we have for steel. We get a flag shape response, meaning that the behavior looks similar to steel initially. So you have a linear part, then there is a yielding and strain hardening that you have. Then once we begin to remove the stress, the path that the stress strain diagram follows is the shape of a flag. So by the time the stress gets to zero, the strain also gets to zero. It's or near zero, but in the idealized way, it's zero. So it's about, you can dissipate some energy here, and yet do not have permanent strain. So then the question is, why not combine these two materials, the ECC and the SMA? Now, I realized that the speaker before me was going to tell you about ECC in a lot of details, so I did not. I'm not going to get into that. It's already covered. It basically is a grout that's got sand in it. It uses polyvinyl alcohol fiber. That's the one we have been using. It has a nickname of bendable concrete, as you see at the bottom of this slide, the little slab that has bent like that. And the primary characteristic that makes it important, makes this material appealing, is its tensile strain capability, tensile strain hardening, and the ability to go to relatively high tensile strains, much more than what you get in conventional concrete. So what you see here is one of our test results. We saw strain capacity, tensile strain capacity of over 2.5%. The literature reports up to 5% that we have. So the material was new to us in the way of research. We say, okay, we are going to try to learn about this material first in our application. So we began to crawl. So the work began with crawling on this subject, and we built some specimens, tensile, flexural, compressive, and we decided to use that in the repair of a column, a large-scale column that we had tested on a shake table with shape memory alloys in the plastic hinge. So you notice that we removed the loose concrete first. So this column had used, in this column we had used conventional concrete. So after the earthquake testing, we removed all the loose concrete, and then we replaced that with ECC. So the slide that you see on the upper right, the photo on the upper right, shows a repaired column. That was the first ECC project that we used. So we retested that column after the repair, and the two pictures at the bottom show you the difference. So the one on the left, the picture on the left, shows the one with conventional concrete at an intensity of earthquake, let's just call it the 3 times ATC at this one. Then when we retested that column after the repair with ECC, the damage is what we saw. in the right side, at the bottom right side. So you notice in this one, we have some surface cracks that we observed here, but nothing like what we have on the other one. So if you go to a bridge site and you see this condition, you say, well, actually, we don't need to close this bridge to traffic. So it became very attractive. So definitely that crawling, through that crawling, we learned that, yes, this material definitely has potential. So then we began to walk by saying, okay, let's just build some more columns and test these. And these are 3 columns that we studied, again, under cyclic loading. The one on the left side is conventional steel and concrete. The one in the middle has shape memory alloys and concrete. So here we did not use ECC in the middle one, but the one on the right side, we used the ECC and SMA. Again, you notice that the damage is substantially less than what you see in the conventional concrete. So we were convinced that, yes, this ECC is very effective in controlling the damage. Now you say, well, the basic attractive characteristic of ECC is its tensile strain capacity, but that having that tensile strain capacity prevents the cementitious material from prevents damage in it, even under compression. So when we have cyclic loading, we see that advantage here. So in the way of force displacement or force drift ratio, which is a measure of how successful a design works, we saw that, well, in both cases, we did have good performance in terms of dissipating the earthquake energy. So a well-designed conventional column exhibits the picture that you see on the left side. This is what we measured in our column test. And the one on the right is the one that has ECC and shape memory alloy. Again, a great deal of energy dissipation, but that flag shape response of shape memory alloy that I mentioned is maintained. Now, if we look at the residual drift, remember one of the damage types that we try to control was to control residual drift. So if I show residual drift on the vertical axis and the maximum drift at the horizontal axis, a conventional column exhibits very high residual drift. When we combine SMA and ECC, we notice that residual drift drops by a factor of 6. This is about 1/6 of the conventional column. But the one that has SMA and ECC is somewhere in between. Still, shape memory alloy brings the column back, but the fact that we didn't have ECC in that column still contributed indirectly to residual drift. In other words, ECC was the solution here. We kept walking. We kept walking by saying, okay, well, what if we use ECC in segmental columns and in other, again, seismic loads, because this is the kind which is attractive for accelerated bridge construction. So here you notice a conventional concrete that was used in a segmental column versus ECC. Again, you see quite a bit of damage in the conventional column, but the damage in the one in which we use ECC in the segments was a lot less and certainly controlled and easier to repair. Then say, well, let's start running now. Now that our level of comfort has increased quite a bit with this, we decided to compare ECC with UHPC in building and testing a large-scale 2-column bridge bend and testing it on a shake table. So the figure on the upper left shows the pier model, and the one below that shows the segments. So in these segments, again, this was part of an ABC, Accelerated Bridge Construction project that we did. So the columns are prefabricated, the cap beam, the footing, they're all prefabricated, then they're all connected later on. The most critical part of these columns is the upper part, right under the cap beam. So in one column, we use UHPC. In another one, we use ECC. The idea was, well, let's compare them and see how well they do. So if you look at the pictures on the right side, the upper one is for UHPC and the lower ones is for ECC. The damage in the plastic hinge was relatively low in both cases. However, if you look carefully, you notice that for the UHPC, the damage extended into the cap beam. And that's a no-no. That's in seismic design of bridges. We do not want any damage in the connection or extended into the cap beam. The much higher strength of UHPC actually forced the damage somewhere else in the structure. So this is one of those rare cases where the better, the more is not the better. In other words, the higher strength of UHPC was not beneficial. Now I'm going to show you a video clip of that last test. So we have ECC, the one on the left, in the plastic sheet we have ECC. The one on the right we have UHPC, and we are going to shake this. And I hope there's enough bandwidth that you can see the video. And if you look carefully, for the column, the UHPC column, you'll see that pieces of concrete falling off the connection as we go to higher motions. Let's take a look. So in this case, the lower flexibility of ECC and its lower strength helped to have better performance and meet the design objective, which was not to have damage in the cap beam and in the joint. Then we decided to keep running, but this time we applied that in a 4-span bridge. This was a 110-foot bridge model that we tested on shake tables at the University of Nevada, Reno. And we had a variety of details here at the different columns, but I'm going to focus on the one where we had ECC and unconventional concrete on the same column. This is the shake table testing of this bridge. Most of the earthquake tests that we did here were bi-directional, and the bottom of the column were subjected to bidirectional flexure, whereas the top was essentially subjected to unidirectional flexure. And despite that, I'm showing you pictures of a column in which at the top we have conventional reinforced concrete, and at the bottom we had ECC. So even though we had harsher loading on the ECC one, again, we saw better performance. Having convinced that ECC could work well in controlling the seismic damage, and considering the relatively high cost of the first type of shake memory alloy that we had used, nickel titanium, we decided to look at alternative shake memory alloys. This one made with copper, aluminum, and manganese is a lot less expensive than nickel titanium, has lower strength. And there were some preliminary tests that had been done that showed that, yes, there is good potential for this material. So we decided to adopt that in one of our projects and use the material copper shake memory alloy in combination with ECC again, and built a column, large-scale column model, and tested on a shake table. And we decided we went all the way to 3.5 times the design earthquake. And at the end, this is the kind of damage that we saw. Again, recall that this is way beyond the design earthquake. So we wanted to establish the limit. So the damage still under the design earthquake, even twice the design earthquake, we had very little damage, just some minor surface cracking. So with that level of comfort increase, we decided to fly now. So the flying came with implementation of SMA ECC in a showcase bridge in Seattle, Washington. This was a project that partial funding was provided by the Federal Highway Administration through their IBRD program, and the Washington Department of Transportation, their vision and interest in adopting new technologies and implementing it was really admirable, and we really enjoyed being able to be part of this and seeing this project this concept was implemented in the SR-99 off-ramp bridge in downtown Seattle as part of the Alaska Way viaduct replacement. The bridge is a three-span bridge, 180 feet the central span, and 110 feet on the sides. Then this precast box, post-tension spliced top girder that you see over here had single column piers. The columns were 5 by 5 square, but they had a round core. And in the plastic hinges of these columns, we used sheet memory alloy combined with ECC, because by then our comfort level was way up there. Now there were a couple of additional work that we did, the research we did before we actually implemented that. First of all, in previous projects, we had changed the nickel titanium into a dog point shape, and we put it in columns. But we said, well, what if we don't do that? What if we use a different kind of couplers, headed rebar couplers that you see at the bottom of this slide? This way, we don't have to shave away a very expensive material. Nickel titanium is very expensive, so we're going to make full use of the cross-section used in this material. Another one, given the fact that SMA nickel titanium is expensive, so what if we shorten this? Can we still get good response? So we did some optimization essentially for this project before it was implemented in the bridge. And here you see that the picture of the column cage with nickel titanium bars at the top, and you clearly see the headed bar couplers at the top, and we had at the bottom, because we don't need to use these SMAs over the entire length of the column, only in the plastic hinge. So in the plastic hinge, this is where we have the SMA bars connected to steel bars at the top and the bottom. And this bridge was completed, was open to traffic February 2019, about 4 years ago. And so it's out there. And I'd like to mention something which was important here. We received a lot of awards for this project. And I'm saying that because the selection committees for 3 of the 4 awards that you see listed here are engineers. They're mostly practicing engineers. They were not researchers that were impressed with the research. They were engineers. And to me, that is an indication that a lot of progressive engineers are out there in various forms, various positions. We certainly have dealt with them in Caltrans in WashDOT and Nevada DOT, Utah, Oregon. And the fact that they picked this project for an award, that tells me that yes, there is an open area, and there is the openness to accept and adopt new technologies. Now, we are continuing our work through a current project. It's a pool-funded project led by Federal Highway Administration and Washington Department of Transportation. We're in the first phase of it, looking at a variety of shape memory alloys, including copper-based shape memory alloy because of its lower cost. There are a new generation of nickel titanium bars that are coming. Some are stronger, therefore we can reduce the amount. Also, an iron-based memory, shape memory alloy that we are also exploring. So in phase 1, we are looking at material characteristics, low cycle fatigue characteristics of these, and we are going to do a lot of moment curvature analysis of the various columns. And the hope is that once we get satisfactory results from phase 1, we're going to go to a second phase where we're going to do large-scale column tests and extensive analytical studies and developing design methods so that WashDOT or other states can take this and adopt it and deploy it in the field. The message that I would like to leave you with is that we civil engineers, transportation engineers, we need to be open to adopting new materials for better performance of our structures. We know the limitations of steel and concrete, and we don't need to abandon them, but where it makes sense, at the locations where it makes sense, we should be open to these. And there are indications that we have many professional engineers, many engineers who are open to that, and we researchers should work with them to implement these. That was my last slide. Thank you so much for your attention.
Thank you very much, Dr. Saiidi. That was excellent. We really appreciate it. Okay, let me just share this. 1 second. Okay, now we'll introduce our next presenter, Dr. Craig Newtson. Dr. Craig Newtson is a professor and interim department head for the Civil Engineering Department at New Mexico State University. He received his Bachelor of Science and Master's of Science degrees in Civil Engineering from the University of Wyoming and his PhD from the University of Washington. He has been an active researcher in concrete materials and structures for more than 25 years. For the last 6 years, Dr. Newtson has served as an Associate Director for Tran-SET, a regional University Transportation Center funded by the U.S. Department of Transportation. Dr. Newtson's research interests include concrete material topics related to special mixtures, mechanical behavior, and sustainability, as well as behavior of reinforced concrete structures and non-destructive testing of concrete materials and structures. Dr. Newtson, I will turn it over to you now.
Right, thank you, Dana.
Okay.
So the presentation will be about a UHPC overlay that we installed on a bridge deck in Socorro, New Mexico. This was the culmination of years of research. Really, we got started doing UHPC research at NMSU back in about 2006. And the thing that we do differently at NMSU than at most institutions is that we look at non-proprietary mixtures, and we have done that from the very beginning. We've never really been active on proprietary mixtures like ductile. We make comparisons to them, but we really haven't looked at that as a long-term solution. We believe that long-term, in order for UHPC to maximize sustainability, it's got to be done with local materials. So that's really where we have focused. So when we look at the researchers here, it's really a list of people who worked on both NMDOT research projects and Tran-SET projects. The research was really funded by both agencies kind of in parallel from about 2017, right up until installation of the overlay. For the NMDOT research projects, my co-PI, Brad Weldon, was the PI on those projects. For the Tran-SET projects, I was the PI. Brad Weldon was my co-PI. On the NMDOT projects, he was PI, I was co-PI. Andres Alvarez and William Toledo are the PhD students that have worked on the projects with us. William working with me and Andres working with Brad Weldon. And as I go through the talk, I'm gonna start off with some background, just talk about kind of what led to this project, because quite frankly, field implementation projects don't just show up on the radar. There's a lot of work that has to lead up to them. I'll then talk about Bridge 7032, which is the bridge that we actually installed the overlay on. We'll talk about the preparation work prior to installing the overlay, a lot of training associated with getting a contractor who had never done a UHPC project before up to speed on just exactly what needed to be done and how to do it. I'll then talk about the overlay construction, talk about things that went well, things that we identified during the construction that needed to be improved, and changes that we made. And then I'll finish up with lessons learned, basically advice that we would give anyone who's looking to perform this type of project in the future. So non-proprietary research started at the time I made up the slide, it was 2008, but I've gone back and looked at what we were doing, and it actually started in 2006 with a little bit of funding from a private company. By the time we got to 26, well, in 2009, we initiated funding with NMDOT. In 2012, the UHPC research that we were doing with NMDOT was identified as one of the, what they call the Sweet 16, one of the top 16 important research topics in the nation. And then in 2016, our work had progressed to the point where we did this little channel girder bridge over an irrigation canal in southern New Mexico. And when you look at that bridge, the right span is UHPC channel girders. It's a shallower superstructure than what you see on the left span, which is high performance concrete. So just a little bit of a comparison there between the two spans, and we've monitored that since construction. And basically about the time that construction finished, Tran-SET was funded, and the first year project at NMSU was to basically start looking at overlay applications for UHPC. And in that first year project, we did a lot of bond strength testing, basically trying to make sure that we could get UHPC to adhere to the substrate concrete. We had some channel girders left over from the construction of the bridge, so we prepped the surface on one of those channel girders, applied a UHPC overlay, did some full scale testing in the lab, just to make sure that we were going to get nice behavior with the UHPC overlay. And then in year 3, well, year 2 was another bonded UHPC project, basically looking at shear keys between channel girders, trying to keep them bonded. And then year 3 was the field implementation project for the bridge in Socorro. And originally the overlay was supposed to be placed in 2019. That got delayed due to issues related to letting the project. So it got rescheduled for 2020, and then the contractor ran into delays on other parts of the project. And it was actually 2021, late spring, April, by the time we actually got the overlay installed. So the bridge is located at exit 150 on I-25 in Socorro, New Mexico. This is the major interchange in Socorro. The superstructure is a multi-cell box girder. It's got 2 lanes of traffic on top of it, and there is a low median between the 2 lanes of traffic. And the total length on this bridge, I'm going to say it's approximately 300 feet. I believe it was 302, if I remember the numbers correctly from the drawing. Kind of a big project for a pilot project, a first effort with local material, UHPC as the overlay material. So that's one of the things that we're going to come back to, is just the size of the project. So the existing deck, first thing we did was go out and kind of survey that, see what kind of issues they had. There were a lot of transverse cracking, basically thermal cracks in the deck. The deck was tined after construction or during construction. The full depth cracks, they were, you could see them even from inside the multi-cell box girder. And then as part of the project, the contractor was required to perform some hydro demolition to remove the surface material. once they got started on that surface concrete removal, they found that they punched through in several places. This actually caused them some delays because to bring the existing deck back up to the original elevation, they basically had to form the inside of the cells for the multi-cell box girder. And in the design for the rehabilitation of this deck, they were to install an HPD layer to bring the deck back up to original elevation. That surface was to be tined, and then that surface was to be prepped, and the UHPC overlay was to be placed on top of that HPD layer. And the HPD is just high performance deck concrete. So actually kind of a 2-layer overlay system from the existing concrete. There was also some work to extend the deck horizontally, laterally, which really doesn't play into the project as we performed it. So for the UHPC mixture, we submitted a mixture to NMDOT for the project. The key point here was that we wanted a mixture that was thixotropic. There were some slopes on this bridge that were 7%. And when you put the UHPC down on that surface, you don't want it to run by itself. You don't want a self-consolidating concrete type mixture, but you do want it to flow once you provide some excitation. So it should be stiff enough to hold its form until you hit it with a vibrator. And it's basically, as soon as you touch it with the vibrator, it should flow readily. So we got that. We got the properties that we wanted with the mix design there. Target slump was 7 inches. Target spread was 10 inches. We had the ingredients down here in the mix design, and basically what we were targeting was minimum strength for UHPC, 17,000 psi, and our mix was at like 17,320 psi. So we had a mix design that was functional for us. We then went to, well, the project was let, and during the letting process, it was decided to enforce by America, which kind of forced us to change our steel fibers. Our steel fibers had at one point been produced in the United States, but that plant had shut down. The fibers that we wanted to use were now produced in China. Those were not going to be allowed, so we needed to perform some work to come up with a different fiber. In our case, Brad Weldon had an old mix design that he pulled out with a different fiber that was produced in the United States, and that was the fiber that we used as the replacement. Contractor got the bid, and the contractor was a contractor who had never done UHPC work before, but as part of the contract, NMDOT required that the mock placement be performed prior to construction so that the contractor would demonstrate proficiency in basically everything that needed to be done for the project. As the time for the mock placement approached, NMSU offered to work with the contractor to get them prepared for it. They declined that offer. So when we showed up for the first mock placement, we basically spent that day working with the contractor about how to batch UHPC. So we had specified dry sand. The contractor didn't adjust for the moisture that was in the sand at the batch plant. So the mix was much more fluid than what it should have been. Basically, we had to work on adjusting the batch quantities, trying to get the contractor just dialed in on how to actually mix UHPC. Really long mixing times, stuff that typical contractors are not prepared for. Anyway, that mock placement was not productive. It was entertaining, but not productive. Although the contractor did gain an education. They scheduled a second mock placement. They kept bogging down the mixer. Basically, they want to mix as large a quantity of material as they can. And the mixers, it's just a difficult material to mix. You've got to have more energy per unit volume than with pretty much any other material that you might try to mix, especially once you get the steel fibers in there. So basically we spent that mock placement dealing with the contractor, basically trying to get their mixer to mix a larger batch of concrete than it was capable of. So basically we just kept downsizing the batch until they actually got something that would mix up. Again, an educational opportunity for the contractor, but they didn't want NMSU to just come and work with them by themselves. They wanted to try the mock placement, hoping to pass every time it came up. So third mock placement. This time, everything actually went pretty well to start. The slab was maintained at saturated conditions. They batched the UHPC in a manner that was perfectly acceptable. The problem was that after they batched the first batch of UHPC, they then allowed the substrate to dry. So everything looked good where the substrate was wet for that first batch. But after that, on a dry substrate, they didn't get bond. However, NMDOT accepted the mock placement. Even though there was no bond, we understood the reason why. The contractor understood the reason why. So we were thinking that we were ready to go to construction. But that was in October of 2020, and they were still working on trying to get the HPD layer placed on the deck. We got to Thanksgiving and they still did not have the HPD layer down. They had it down in one direction, not the other. So I think they had the eastbound done, but not the westbound. And then they shut down for the construction. They basically ended the construction season. They came back after the new year in February to get back to work, and the crew that they had for the calendar year of 2021 was almost completely different from the construction crew that they had in 2020. I think there were 2 people that were the same from the 2020 crew that went through mock-up number 3. So with a completely new crew, they decided to do another mock-up, and everything went smoothly for the most part. They still didn't actually keep the substrate saturated. They just wanted to make sure that their crew was able to place the concrete, place the UHPC. For the most part, everything went smoothly. Again, there was a lack of bond with the substrate, but everyone knew what the issue was, and the contractor gave assurances that they would take care of this on the actual construction project. So once they got the HPD layer down, we needed to do the surface prep. What you want on your surface is some exposed aggregate. So when you look at the picture here and you see some exposed fine aggregate from the ceramic bead blasting, that is kind of bare bones minimum as to what you want to see for exposed aggregate. So we accepted that as adequate, and it was really minimal in terms of acceptability. After that, it was just a matter of keeping it saturated, and on the job site, the contractor actually did a really nice job. Every placement, the contractor did a really nice job of keeping the substrate saturated, the HPD layer saturated. Construction began in one corner of the bridge, and once construction started, for the most part, that progress was good. There was an issue at the very beginning with some ponding, but aside from that, it went smoothly for the most part. There were 105 batches of UHPC produced. Each one of those batches was a little bit more than 3/4 of a cubic yard, so 0.77 cubic yards, which kind of gives you an indication of how big the project was. 1-inch overlay for basically 300 feet in each direction. We ended up rejecting 7 batches, and I guess at this point it's worth pointing out that we specified the mix design. So it was a prescriptive specification. NMDOT made that choice feeling like they had to on a pilot project with non-proprietary UHPC because the contractors wouldn't be able to come up with a mix design on their own that would facilitate a performance specification. So since the mix was prescribed, those 7 batches that were rejected, the money for those batches came out of NMDOT's pockets, and it was NMSU doing the testing on site that rejected those batches. So when we rejected those batches, we were acting as agents of NMDOT, and NMDOT had the liability for paying for that concrete. So it's just the nature of a pilot project, an implementation project. It's not what you would want to see long term, but it certainly served the purpose that we needed it to serve at the time. The 7 batches that were rejected, almost always because the mixer bogged down. I think 6 out of the 7 were bogged down mixers. One of them, I think they missed an ingredient. The workability came out very, very out of line. Yeah, that's an OSHA picture right there. Put the shovel in moving equipment. In terms of material handling on the job site, cementitious materials were bagged separately, or we required that the cementitious materials be bagged and the aggregate bagged separately, sand. So the cement and fly ash were the cementitious materials that were stacked. Silica fume was actually used straight from the sacks provided by the manufacturer. And basically what the contractor did was they chose the batch volume so that it would be an even number of silica fume sacks. Everything worked well on the mixers. They basically set the mixers up at one end of the job site and then placed concrete from the far end toward the mixers as the pour progressed. So at the very beginning of the first placement, there was a ponding issue, a little bit of excess water. It was a small area, maybe 100 square feet total. In testing after construction, we actually don't see any issues in that area. Everything looks great in that area, but there was some concern. Basically what they had was a hose that was leaking and running down and ponding at the low end of the pour. Everything turned out well off of that anyway. So the mixers were set up at one end of the job site. Placement progressed from the far end back toward the mixers, and basically the 0.77 cubic yard batches would fill 2 of these 16 cubic foot buggies, and the buggies just transported the UHPC to right in front of the screed, put it down on the ground, and then it was shovel work, some hose, and then vibration to spread the UHPC out in front of the vibrating screed. So there's the spreading operation, vibrating screed, and the little bit of work by hand, not something that you want to see with concrete in general, and certainly not with UHPC. It's extremely difficult to work by hand. But around the edges, there was some handwork. This area right behind the screed is the area that was kind of important to us. When things went well, there was curing compound getting placed, getting sprayed right behind the screed to control moisture loss. And then right behind the curing compound application, we wanted to get plastic down. When that happened, things went well. At the very beginning of the placement, that wasn't happening. So we placed the overlay in 4 placements. The first placement, probably the first half of it, the plastic wasn't getting down fast enough behind the curing compound, and there was cracking in that region, and I would call that cracking moderate. But I'll show you a picture of it shortly. When it went well, the curing compound was going down right behind the screed, and the plastic was getting put down no more than a handful of minutes behind the curing compound. When that happened, everything went well. At worst, we got isolated cracking. You could walk several yards of the deck before you could actually find a crack. So things went well when this practice was incorporated. The original contract called for a continuous placement from one end of the bridge to the other, no construction joints. We didn't want, the NMDOT did not want the joint, specified that in the contract. The problem is that there will almost always arise a situation where you actually have to install a construction joint. And you better have a plan. Well, you should have a plan. It's not, in this case, there was no plan for where to put it once we realized that the contractor just didn't have enough material to finish the eastbound lane on the first placement. So it was a discussion on the job site to choose, do you want it do you want it above the support in a negative moment region where the joint's going to open? Do you want it in a positive moment region where it should have some compression? Or do you want it just a few feet off of the pile cap so that you can have it near an inflection point? In the end, we chose something near the inflection point, just try to make it stress neutral. But when you're doing this and it's the middle of the night and you're not going to get anybody from the bridge design group on the phone to see what they want. That was really the issue. It would have just been more comfortable for everyone had there been a plan ahead of time. Talk about cracks, and in that first portion of the first placement, it's the same crack in both pictures, but that's basically what the cracking looked like. And it wasn't tight. I mean, you don't see any other cracks in this photograph, which actually encompasses quite a bit of area, but it was just moderate. It wasn't isolated, but it was not densely cracked either. And it really just needed the plastic to come down on top of the curing compound more rapidly. So at the end of the project, we came back and looked at bond strengths, basically performed some thermal imaging to try to identify where some delaminations might be, if there were any. Also used chain drags. That's the lower tech thing, not nearly as attractive as the color photos from the thermal imaging, although the lower tech stuff is oftentimes more useful. There were 4 places where we felt that there might be delamination. And when we did pull-off tests, we looked at 2 of those locations, the first and the fourth. The fourth actually was delaminated, and that particular area was like a 2 foot by 2 foot section. So about 4 square feet that was delaminated. Area number 1, it didn't meet minimum strength, but it was not a 0 strength. It was not completely debonded at that location. When we look at the average strengths, we were happy with what we got there in terms of the bond strength between the UHPC overlay and the substrate. So by and large, it looked good. In terms of lessons learned, the first piece of advice that I would give anybody is start small. This bridge in particular required greater capacity than the contractor had. So the idea of doing the entire eastbound lane in one continuous pour exceeded their labor capacity and exceeded the materials capacity that they prepped prior to construction. Doing something smaller would have facilitated a little bit more control over things like not having a construction joint. Second thing is start with a more robust mix design. We had a very lean mix design. We had really put a lot of work into trying to optimize sustainability and low cost so that we drove our strengths down to just above 17,000 PSI. And then when we enforced Buy America and we had to change our fibers, it required more work than it should have. if I could go back and change something, we would have started with a more robust mix design so that changes like that wouldn't have so much of an effect. Number 3 is try to avoid prescriptive specifications. And honestly, at this point, I would say that there's no reason not to just go to performance-based specifications. When we do our non-proprietary mix designs, we make them publicly available. We don't consider them to be our property at all. We publish them. We consider them to be freely available. Any contractor can look at them and work up their own mix design with their local materials that they're using wherever they are. There's no reason why performance specifications can't be used at this point, in my opinion, for non-proprietary UHPC. Require multiple mock placements. This one was golden for us. You really have to hold the contractor to the point where they have to demonstrate proficiency in every little thing that has to go right on your implementation project. That one was crucial. Have a plan. Require the contractor come up with a plan that shows they've got the batching, mixing, and placing capacity to actually perform the work in a conservatively timely manner. Ours could have gone smoother, but that was largely due to the contractor. It's a combination of the size of the project and the contractor's capacity. On the actual construction, the curing really has to follow immediately behind the screed. Curing compound down immediately behind the screed, and the plastic on the curing compound no more than a handful of minutes behind that. And then have a plan for cold joints or construction joints. That's just one of the things that was specific to our project. Honestly, I don't see the construction joint as being a big issue, but it was against what we wanted in the contract. So in that sense, there were at least a couple of people who were unhappy with the fact that it happened. Anyway, that was the project. That's what I've got to share, and I guess we'll turn it back over to Daniel.
Okay, thank you very much, Dr. Newtson. That was amazing. Thank you. Well, this is 1 second. So this concludes the presentation portion of our webinar. Now we'll start receiving questions from the attendees. I think we already have one question here. Let me get back to the questions. Text 1 second. Okay, I see one question here. It's for Dr. Craig Newtson, right? Was the curing compound being applied at New Mexico at NMDOT's specified application rate? Like if you have one?
Yeah, NMDOT did not specify an application rate and did not check the application rate. It was basically just the project manager assessing it visually, and NMSU basically doing the same thing, a visual check to make sure that there was adequate coverage, but the rate was not specified or measured.
Okay, that was one question from the audience. There's another one here. 1 second. Okay, there's another question for Nor-Yusin. It's a bit more descriptive way explain. It says, my question is a bit more in a descriptive way of explaining that if ECC is alternatively termed bendable concrete, as mentioned by Dr. Arce and Dr. Saiidi, then why does not include coarse aggregate, a major component of concrete? Okay, that's the first. I think there's more than one question here. That's the first question that they're using.
I'll be happy to answer the first part of the question if you want, Daniel.
Okay.
Yes, this is a very good question. Of course, concrete has coarse aggregate, otherwise it's a mortar, so you could call it bendable mortar. But the reason is because of the design criteria for these materials. As I was mentioning, the design is based in fiber matrix micromechanics and also fracture mechanics. And what these concepts tell you is that you need multiple things, but one of the things you need is a cementitious matrix with a very low fracture toughness, so that these cementitious matrix can easily crack and produce these multiple cracks. If you use a coarse aggregate, the fracture toughness of the cementitious matrix go very high. So this is not conducive to this multiple cracking behavior that gives the ductility. Furthermore, if you have coarse aggregate, fiber distribution is a big problem. These systems have about 2% by volume content of fibers. So whatever the aggregate is, there's no fiber there to breach this crack that will happen across the aggregate, right, at the interfacial transition zone. So that's a twofold reason why you don't use large aggregates in the ECC. With all that said, there's some very recent research that has been done that for the very first time, some bendable concretes with some coarser aggregate is being made by using some very high performance fibers and doing some interesting work there. But overall, you do not use coarse aggregate in ECC for the reasons that I mentioned, and it's very, very, very complicated to achieve the performance of the ECC with coarse aggregate.
Okay, perfect. Thank you, Gabriel. There's also a question, but this is for Dr. Saiidi. The thing is, Dr. Saiidi asked me, told me that he would have to leave early. So I will forward this question to him and include you in the email to the person who asked the question, right? Well, yeah, that was directed for Dr. Saiidi. Okay, I also have a question for Dr. Newtson regarding his project. You mentioned that you had some cracks a little after the overlay was cast, right?
Yes.
Do you think that using UHP ECC might be a solution for avoiding this kind of issue?
I think in New Mexico with an extremely arid climate, leaving fresh concrete with really high cementitious contents exposed for more than just a couple of minutes is going to be problematic regardless of the material. Now, in the case of ECC, I believe that it is more flexible. It's more likely to that's going to help you mitigate some of your cracks. So I think you've got some nice potential there. But in our climate, I suspect that you would still see some cracking. Okay.
Yeah, it might reduce, like the cracks might still appear, but it might reduce the size, right?
Yes. Yeah.
Okay. Okay. Do we have any other questions from the audience? Let me see. I'm going to check. Yeah, here. Just one more. Okay. Can pulverized recycled glass be used as sand replacement in ECC? This is for Gabriel.
That's a very good question. I'm not aware that this has been evaluated. Maybe there's already some research on the topic, but just thinking about the type of material that you're proposing, I think it would be possible to use that. I have conducted previous research on some alternative forms of fine aggregates, and mainly what you want is just a fine particle. So if that pulverized recycled glass has a particle size, the maximum particle size less than 1 millimeter, it's suitable for the ACC. Granted that it's not going to deteriorate inside of the cementitious matrix, but I don't think this is going to be the case with the pulverized glass. maybe you can have some type of reaction. I know some pulverized glass that are being used now as an SCM. So yeah, it would be interesting to see. I'm not aware of research on this topic, but it's an interesting question.
Okay. I also have a question for Dr. Arce. I wanted to know, is the ECC for culvert repair being widely implemented throughout Virginia right now, or not yet?
So so far we have had 6 projects, but we are starting to implement more of these. So what we have done so far is 6 repairs, but we envision this as more widely applied. And actually, we have talked with many different districts here in Virginia, and they like the repair. And I believe we're going to see more of these in the next coming years.
Okay.
Just to finalize the response, you need to also understand that this was originally a research project. The first repair that was done was 5 years ago. So first we will try to monitor, how this repair is working before, this is more widely adopted. But so far, 5 years have passed, repairs look good, and I think this is going to be more and more utilized.
Yeah, you basically need a proof of concept that takes some time. Yeah. And okay. Do we have any more questions from the audience? Let's see. Okay, I do have another question for Dr. Newtson. Are there any other plans to implement UHPC again on another bridge soon?
Not soon. Well, NMDOT right now is still using UHPC for key applications, closer joints. For overlays, after we did the non-proprietary, they wanted to do a proprietary UHPC overlay for the sake of comparison. So that will be their next one.
Okay. Sounds good. And okay, we have another question from the audience. It's for Dr. Newtson. Is NMDOT considering using UHPC type materials for repair applications? Well,
for the overlays, yes. So our year 2 Tran-SET project was for shear key applications between superstructure elements, and for original construction, NMDOT likes it. For repair applications, not so much. It seems like an expensive way to only buy a few more years. Once the shear keys start to degrade, it's not necessarily a great way to using really high quality materials to repair those shear keys isn't necessarily the best alternative. The idea of UHPC is that you're going to get long-term durability. That's how it really pays for itself. And if you're only buying 8 or even 25 years, that's not an application that would be beneficial. They are interested in it for beam repairs. We have not looked at that yet here at NMSU, but that is an application that the Bridge Design Group is quite interested in.
okay. Thank you, Dr. Newtson.
Sure.
Okay, I think we don't have any other questions. Still, if anyone in the audience has any further questions, you can always contact us at Tran-SET, the email which I used to contact you. And okay, again, I think we can end right. I would like to thank our presenters for their time and technical presentations. And I want to thank also all the attendees. Please let me know if you have any questions about the webinar series and about Tran-SET. And otherwise, have a great rest of your day. Thank you so much.
Thank you very much, Daniel.
Thank you, Daniel. Thank you to the whole LSU group. It has been wonderful working with you guys for the past 6 years.
Yeah. No.
Thank you. Very nice to see you, Dr. Newtson.
Yeah, it's good to see you again.
Yeah, it
Thank you.
was really good to hear about your project right now. I was really interested in that. Thank you.
Right. Thank you all.
Have a good weekend.
Yeah, you too.